We are now going to start thinking about current, and specifically we're going to start from a very basic understanding of what current is before we jump into more complicated topics like circuits. So we're going to start with our parallel plate capacitor and think about the fact that we have a negative plate and a positive plate. So initially, those electrodes have separate opposite but equal magnitude charges on them. And our model for really the ideal parallel plate capacitor, ideal air surrounding it, is that these stay charged indefinitely. So they're staying charged and the charge just sits there. So in this model, we don't think about the charge suddenly jumping from one to the other. That rarely happens. And whenever we think about that within a physics context, we are explicitly talking about discharge occurring. So our model is that they stay charged indefinitely. However, if we take a wire and we connect one plate to the other, we see that the capacitor is going to discharge, that the charge is going to, we could say, neutralize, that the positives and negatives now have a path, right? They can get from one plate to the other. And since they're attracted, they're going to want to get from one plate to the other. And so we go from having a whole lot of charge to having fewer charges. So we say that this is a current, that a current is flowing through the wire. We're going to use eventually a symbol I for that. But now note that what I showed here would be, say, for instance, the minus charge is going that way. So we're not actually going to use capital I for that. What we're going to introduce initially is lowercase I subscript e. This is going to be our electron current. So we can think about all of these electrons jumping off the plate, coming through the wire, and neutralizing with these positive charges. So that's what we assume is happening because eventually we don't see that there's any charge left on our capacitor. There's no electric field created, there's no potential difference. But how else, other than looking directly at the capacitor and seeing that its charge has changed, can we infer that there is a current? And this is important because keep in mind that physics is fundamentally an experimental science, that a lot of what we've been talking about so far with fields are not directly observable. Potential can be measured, forces can be measured, but a lot of what we're talking about has to be inferred. So current is interesting because we can directly see evidence of it, but we're going to need some additional techniques before we can actually measure it directly. So the two ways that we know that there is current, so these are indicators of current, is that the wire itself will get warm if a current is flowing through it. And one way you can think about this, if you've ever worked with an electric stove or an electric range, that the reason that that burner gets hot and glows red is that you're actually passing a current through it. So things get hot due to current flowing through them. And we'll talk a little bit soon about why, but that is one of our indicators. That if we see a wire and it seems warm to the touch compared to its surroundings, that a current is causing that. The second, and we're going to have to wait a while before understanding this in detail, is that a current causes a compass needle to deflect. Now, you might just know that a compass tells you something about direction. What does that have to do with current? Eventually, we're going to learn that this has to do with magnetism, actually. But for now, these are our two indicators. We're going to learn about the cause of the wire getting warm, and in a few chapters, we're going to be able to relate this to magnetic fields and understand why it causes a compass needle to deflect. But what you need to take away from this is that we can fundamentally know if a wire has a current in it or not through very simple means. And these were techniques available hundreds of years ago, well, 800 years ago. And so really the understanding of some electricity and magnetism comes from these two techniques, especially the deflection of compass needles. As we think about our current, we need to remember that electrons are our charge carriers. We're thinking about a metal, so we're thinking about a conductor, and the whole is electrically neutral. So having a current flowing does not necessarily mean that there's a net charge. We're about to talk about it in terms of a net charge, or charge distributions, but let's remember that conductors can still be electrically neutral and carry a current. What that simply means is that every positive ion has an electron that corresponds to it somewhere. So for every positive ion, there's an electron. But the ions, these positive ions, are more or less in fixed positions, but our electrons are able to zoom about as this picture shows them doing. So the electrons are more or less free to move around, and so those are going to be the way that charges move from one place to another. We sometimes are going to think about positive charges, but at least in a metal, it's actually always the electrons moving. If you have an ionic solution, so like a liquid bath of salt water, in that case you can have positive carriers as well, but typically in this class we're going to work with metals where our carriers are electrons. We need to define a quantity called drift speed. And drift speed is the speed at which our sea of electrons, i.e. the free electrons in our metal, are drifting down the wire. Now what we're about to introduce is a reason that they're going to be drifting down the wire, but we need to think microscopically about what's going on. So there's a certain number of electrons per cubic meter of wire, and again here we're thinking about free electrons, the electrons that are able to move through our wire. So this is a density, Ne. So we have a number density of electrons, and then we have some cross-section of the wire. So you imagine taking all of the electrons in this area and saying that they're drifting with speed Vd. And we're going to define what this means. This isn't the absolute speed that they're moving. They're not all perfectly moving to the right. But over time, just like people filtering from Evans over into classrooms or vice versa, there's some net motion slightly down. So at some delta t later, they have moved some new distance. So the drift speed is simply going to be that average distance moved, or that amount moved over, divided by the time it takes. So this should look really familiar, but we're now going to try to understand in a more detailed microscopic level why they would be drifting, and we'll come back to this understanding later. The reason we care about electrons actually drifting is that this is literally our current. And here we are talking about something special called the electron current. So this is lowercase I subscript e. We're going to talk about current later, which has a different symbol. So note that if you've learned about currents in the past, we are actually talking about something different right now. So that's the number of electrons, number density, of electrons in a material, and then the cross-sectional area of whatever you're talking about. So for instance, if this is a circular wire, this could just be pi r squared, but this could be a square cross-section wire, whatever you want. And then we have that drift velocity. So this is simply saying really how many electrons do you have drifting past a given point per unit time. Right? So electrons, they're flowing, and so this is just like watching the surface and saying, well, how many are drifting past? And since this was a density, you have to multiply it by area. So this is really just, well, how many electrons are going past per unit time? So eventually we're going to relate this back to normal current, but let's think about microscopically why this is happening, what's going on. The cause is going to be, for instance, discharging a capacitor. So our capacitor is going to start with equal but opposite sign charge on each electrode, and we know that our electrons are going to be able to move. So once we put the wire in place, some of these electrons are going to jump out and start marching down. So we see that there's an electron current that is allowing them to move, that's going to be equalizing these positive charges, which are actually just missing electrons. So we know that this is happening, and that is actually the process of discharging our capacitor. So the sea of electrons actually are filling this whole wire. So one thing that's a little hard for me to just show with my annotations is it isn't that we have one specific electron. Let's call that electron, I don't know, Pat. It isn't that Pat is actually moving this whole path until Pat gets here. That isn't what happens. You know, imagine a really crowded mall, and you have some people standing here, and a bunch of people in front of them. As these people move forward, the people at the very front are probably moving forwards too. So the same thing is happening here, that as these first electrons move just into this little spot here, that corresponds to some electrons in the sea of electrons in this wire moving into the capacitor there. So this is really important to remember, that you don't literally have to have one electron from this capacitor make it all the way in. It's just that these first electrons bump into the next ones, bump into the next ones, and so on. And so you're basically pushing a little bit of the C electrons into the other capacitor. So that is part of what allows this to happen so quickly. You don't have to have this electron go super fast. You just need to have the entire thing of electrons shift altogether. So that's the overview of electron current, and next, in the next video, we're going to zoom in and think about this microscopically and understand what's actually causing all of these electrons to even have a drift velocity.